Hello, everybody. 3.1, exponential function. So, little change of pace here in this chapter. It's definitely one of my favorite chapters of pre-calc if I had to rate them. And I think it'd be a good time to start by saying what is an exponential function. An exponential function, there we go, is of the form f of x is equal to a times b to the power of x, where x is any number and a and b are real number constants such that a cannot be equal to 0, b cannot be equal to 1, and b is positive. Let's talk about why. If a is 0, this whole thing goes to 0, right? Because 0 times anything is 0. If b is 1, 1 to any power is itself. So it would be whatever the value of a is, for no matter what the input is. Okay, so, and b being positive, if you get a b value that's negative, your graph's going to be crazy and all over the place and not an exponential function. So, I wrote some exponential function examples. Fx is equal to 2 to the power of x, f of x is equal to 1/2 to the power of x, and f of x is equal to 2 to the power of negative x. All these are wonderful examples of an exponential function. Let's talk about what isn't an exponential function. F of x is equal to, let's say, 2 to the power of x to the negative fifth. Yes, it has an exponent, but no, it is not an exponential function. Big no. No. Okay? The unknown, the input, x, needs to be in the exponent, not the base. Just because you have an exponent as a number doesn't make it an exponential function. It's whenever the unknown is in the exponent. Also, is this it? No, because b can't be 1. I just told you that. Let's graph a couple of these, shall we? So, f(x) equal to x to the power of negative x. If I put 0 in, you'll get 1. 0 to any power is 1. So got 1. If I put 1 in, I will get 6 to the power of negative 1, which, flip it, you get 1 over 6. So about 1 over 6 is going to be less, and then it'll continue going less down here. If x is equal to negative 1, negative 1, 6, so it'll be 6 to the power of 1, which is 6. 2, 3, 4, 5, 6. And then it will continue to increase. And as you can tell, if you picked other positive values of x, it's going to keep getting smaller and smaller fraction, but never touch the x-axis. Let's talk about it here. So I asked about the domain. What's your domain? You can put anything you want in for x. What's your range? It can't be below 0, right? It can't be equal to 0, too. So it'd be 0 to infinity. Intercepts. What's your y-intercept? 0, 1. You don't have any x-intercepts. Doesn't cross the x-axis. Asymptotes. You have 1. For the original exponential function, it's always going to be y equal to 0 unless you have a transformation moving up or down. And I asked for the limits. As you go to infinity, it's getting closer to 0, as we established. As you go to negative infinity, your function is going to infinity because it keeps getting bigger and bigger. In this one, if I make an input of 0, this whole thing will go to 1 because anything to 0 power is 1, plus 1 is 2. I didn't want to draw it there. Let's try again. If I put, let's say, 1 in, 1/4 to the 1 power is going to be 1/4. 1/4 plus 1 is going to be a little over 1. If I put negative 1 in, remember, anytime you get a negative exponent, you can flip it. So I can flip that 1/4 to get 4. Then 4 plus 1 is 5. Negative 1, 5, 3, 4, 5. And then if you pick other values, we're just getting closer and closer to 1 without touching. And this one will go to infinity. So, domain, same story. Negative infinity to infinity. Range, In this case, it's going to be 1 to infinity. Okay, so I'm going to include 1. Intercepts. We put 0 in. What did we get? We got 2. 0, comma 2. Asymptotes, y equal to 1. So we're going to touch 1. Limits are the same as the first one, except for this one right here, except for the one that was going to infinity. When it's going to infinity is equal to 1. Limit as x goes to negative infinity. That's going to infinity. So this is for exponential growth and decay functions, standard without any transformations. So they're all of the form f of x is equal to b to the power of x. For growth, b is greater than 1. For decay, b is between 0 and 1. Okay. Here are everything you would expect in a growth. A growth would look something like this. That being 1, like that. And then decay, that was terribly drawn, but you get the picture. That's 1. Will look something like that. Okay. And all your extrema, intercepts, domain range, all written out there. End behavior, as you see with this one, as x goes to infinity, your output goes to infinity, and as x goes to negative infinity, it goes to 0. Vice versa for exponential decay problems. All right, we're going to do 2 transformations for this function and then this function as well. So list what they are. And in class we will graph them. So this one, we have a negative on the outside right here. Okay, so that means it reflects over the x-axis. And also we have a plus 2 on the numerator. We're adding 2 to the x value, so it's going to be, you're going to translate 2 to the left. Good. And then for this one over here, we have a negative in the exponent, a negative with the x. When you have a negative with the x, it reflects over the y. Reflect over y-axis. And we have a 2 on the outside. So it's going to be expanded vertically by 2. Okay. These are all based off of transformations we did previously in the year. So if you're unfamiliar, I'd recommend you look at those. Okay. The only little difference, and it's not that big of a difference, instead of saying we use a different word than expanded for when you're multiplying by a value bigger than 1. In this case, we are going with expanded. This right here is an important exponential function that you're going to be seeing in one way or another often. So anyways, it's 1 plus 1 over x to the power of x. So I made a table here, which I would recommend you write down as well, so you know where it came from. Where I made the inputs as x increased, what happened? So I put 1 in, you gain 2, and then so on and so forth. And really, then it's if you notice the numbers as you got bigger and bigger, there is less of an increase. Okay, you might have seen this number before somewhere. Okay, this number is base e. E representing Euler's or Euler's. I've heard both pronunciations, and I always hear people correct each other over it. But Euler's, Euler's, however you want to pronounce it, is what this number is called. It's a button or a calculator. I believe it is second divide on your graphing calculator. If you punch that in and get an equal sign, you will get 2.71 numbers, so on and so forth. Okay. What does that represent, you might ask? Whenever you have an exponential function that is constantly growing, we use this Euler's number to denote that, because what's happening in this is that every single moment your exponential function is getting bigger and bigger. Okay, you typically see this with if you're doing geography problems and you're doing stuff with population, right? Uh, because you're not just going to have 100 people move one day um, at every so often, uh, and that's how you're growing. No, people are either moving out of your area or moving into your area um, always, in or out always. Okay, so let's do some examples. First, we're going to do it with money. So, as I said, we're going to talk about money. Here are your two main formulas that you need to know for compounding interest. I'll explain what compounding interest means in a minute. I'm going to talk about what all these variables mean. P is what's called principal. That's the money you start with. That's the money you put into whatever you're investing. R is your rate, your interest rate. It's in as a decimal, so make sure you put it as a decimal. Okay, not as a percent. So if it's 10%, do not put 10 in for R. N, number of times compounded a year. T is a time in years. Okay. A is the amount after time t. All the same ones mean in here as well. Just remember, this is Euler's number. Okay, base E. So that's what they all mean. So compounding interest, what is it? What's the importance of it? Well, compounding interest is probably one of the most important topics you learn in school. They always say, "Why didn't they teach us this in school?" Well, I am not right now. Okay. Compounding interest is so whenever you're investing money in something, okay, um, and you put money in, you earn interest so much interest in a year, right? And then your interest earns interest. Okay, this is how you make a lot of money and can retire earlier than what you expected because you're going to invest money, and then your money that you're investing is going to earn more money, and then you're going to earn more money on both the money you already earned and the money you put in, which is kind of cool. So you're making a lot more money. And also, this is why, and I'm going to do some various examples in class that's going to show you this. It's important that you invest early and often, okay? Because the longer you invest, the more money you have, okay? Which is important, okay? So that bigger that T number is, that the amount of money you can have is going to go so much higher, okay? So that's why they always say invest early and often, okay? Let's do an example together. Let's go down here. So down here, we're going to use the compounding continuously formula, that PERT. It's easy to remember, PERT, right? So we have A equals P base E to the power of RT. So say you're investing $1,000 at 8% interest compounded continuously. How much money will we have in 10 years? Okay. So 8%, if you're investing in, it's your book said bank account. I would love to meet someone whose bank account makes 8% interest because that's just not realistic at this time in our lives. But 8% is a pretty standard for roughly what you can expect if you invest in the stock market over the course of your adult life. Might be even a little low. Because on average it will earn a little bit more than 8, probably 9 or 10, but we're going with 8 for this problem. We don't know what A is, okay? I know what P is. P is 1,000. Base E to the power of R, which is 0.08, and T is in 10 years. Okay. Little tip when you put in your calculator: base E to the power of 0.08 times 10 first. Okay. Do that first, and then multiply that by 1,000. That will get you a solution of $2,225 and how many cents? I got 54 cents. Okay, try putting that in a calculator, see that it matches up. So here's a real world modeling problem. Okay, your book uses these formulas for population. Okay, I've seen different variables used. Um, N sub naught is your starting population. N is just what you end up with after time t. Also with continuous, they use k. K being the rate. Okay, so k is just another variable they use often in rates. You'll see that in other um, application problems through this. So population of town is declining at a rate of 6%. If the current population is 12,426 people, predict the population in 5 and 10 years. So let's try annually. Let's just do 5 years, okay? For both of these, just for the sake of time and we're spending time together. If you want to try 10 on your own, do it. I can tell you the answer, yeah? So you're starting with 12,426 people, right? And you're declining at 6%, which means you're subtracting 6%, not adding. If you're increasing, it would be plus 6%. Okay. Time, as I should have put in time there, it's 5. Same story over here. What are you starting with? 12,426 base e to the power of 0.06 times 5. So you put them in, what do you get? I know I said earlier in the video that usually it's continuously with population, right? But just so you see the difference, we're doing both. Okay, it would normally be continuously though. So continuously, you will have about 9,205 people, and annually, you put this in, you're going to get about 9,119 people. Oh yeah, it's negative. It should be negative 0.06. My apologies. And that will do it. Appreciate you watching, and we'll see you later. Bye bye now.